Hello and welcome to this webcast, How Consolidating Computing Resources Can Democratize Research Infrastructure, hosted by Scientific Computing World and sponsored by Sendio. My name is Robert Rowe. I'm the editor of Scientific Computing World, and our guest panelists today are Robert Henschel, Project Director at Indiana University and HPC Lead at Sendio, Xavier Pillans, Principal Technical Program Manager at Azure, specialized workloads HPC and AI, and Jonas Lindemann, Director of LUNARC, Center for Scientific and Technical Computing at Lund University. Robert Henschel is a technical leader who has worked on high-performance computing for more than 15 years. Henschel has also held leadership roles in higher education and in industry. Robert currently works as a project director at the Indiana University and as HPC lead for Sendio, where he helps oversee the implementation of cloud technologies. Xavier is an experienced principal program manager with a history of working in the computer software industry. He is a specialist in high-performance computing, Azure, and software as a service. Xavier currently works on incubating the Azure HPC on-demand platform, an accelerator to build HPC-ready clusters in the cloud. As director of LUNARC, Jonas manages the operations and development of high-performance computing infrastructure and services. He has a PhD in structural mechanics and more than 15 years' experience with HPC and distributed computing. In today's data-driven landscape, access to high-performance computing resources can drastically accelerate research and development, enabling breakthroughs across a wide variety of diverse fields. However, barriers like costs, high cost, technical complexity, and limited in-house expertise make HPC inaccessible for many researchers, especially those in emerging data-intensive fields and smaller organizations. This webcast aims to address these challenges and introduce solutions that democratize HPC for scientists and engineers in biotech, life sciences, drug discovery, geophysics, and engineering markets such as CAD and CFD. Our panel of experts will discuss strategies for HPC access, the development of user-friendly interfaces, and efficient resource allocation models tailored to non-traditional HPC users. Attendees will gain insight into centralized computing models, which offer significant energy and performance benefits by pooling resources into a shared HPC system. This approach can transform an array of individual systems into a streamlined solution, reducing energy use and operational costs while enhancing computational capabilities for teams lacking extensive HPC expertise. In addition, after the discussion, there will be a question and answer session, which anyone can use to ask our speakers a question. If our speakers do not have time to answer your question today, the information will be passed along to the relevant people so they can follow up at a later date. So without further ado, our first question for the panelists. Why do more researchers and engineers require access to HPC and AI resources? Why do you think this trend is increasing?
I think more disciplines nowadays have access to a lot more data. I mean, you see that in training AI, and you see that in how easy it is to generate larger data sets, which then require larger storage capacity and also more compute resources to process them. So some of the fields of science that in the past could get away with high-powered workstations with multiple high-powered workstations now really have to use HPC resources, not just for the storage, but also for the compute.
I agree. That's the same situation here at LUNARC. We got more and more smaller users that have grown out of workstations and have a lot of data that need to process.
Yeah, and with the increase of GPU powers, you need to centralize those and share them efficiently to reduce and manage your cost efficiently. Muted.
Sorry, my apologies. As you mentioned workstations there, how can a centralized compute environment overcome the limitations of isolated desktops?
I think you can answer that at the university. I think during teaching and education, it's very hard to provide a unified environment. And by having a centralized environment that is remote, all the students and the research get the same environment, and it's consistent and you can use it. There is no diverse, this computer does something differently than other computers. It provides a lot of benefits in that way.
And if you also, since I also work at the university, being able to offer every student access to a high-powered machine, regardless of whether they can afford a high-powered Mac or Windows laptop or workstation, is an important consideration for us as well. So getting people into a centralized environment doesn't just make the support easier, as Jonas said, but also makes it easier for everyone to participate in research.
Okay, does that kind of homogeneity of resources make it easier as a teaching tool as well then?
Yeah, so for example, in a course you have you want to teach parallel programming or processing of data. You can tell the students to load this set of modules, and you know that every student and researcher have the same set of tools, and the material is easier to maintain because you can guarantee that it works every time.
Yeah, we have here at IU as well, we teach a lot of classes that take advantage of the centralized HPC systems. And that makes it so much easier for the professors to get every student onboarded.
Yeah. What about kind of collaboration benefits? How can tools help to enhance collaboration within research teams using HPC, particularly in terms of file sharing, project management, and kind of remote access?
Yeah, so if you take Lunark again, so we in our larger resource, we have a shared storage file system where the users can apply for projects, and those projects can be shared among the groups, and they can use the same tools, remote tools, to look at the data in their shared spaces, and that's very easy to do by just the PI can add and remove users that are allowed to access the data. So that facilitates sharing quite much easier.
Without having to copy the data. That's always an important consideration for us as well. We offer a graphical desktop solution where people can basically connect to a centralized graphical desktop and then can use the tools on that desktop for data management. And that made it a lot easier for not having to distribute the data.
So you mentioned graphical access there. Is that becoming increasingly important for researchers?
I think it's specifically for users that are new to HPC, right? As I said earlier, in the non-traditional HPC disciplines, people are coming from graphical desktops and graphical environments. And when we want to get them into a centralized environment, trying to give them something that looks as close as possible to what they are used to, so they don't have to start from scratch with learning how to be effective, I think is key. And being able to give them access to graphical tools like RStudio, MATLAB, Simulink, some of the graphical CFD tools that are seamlessly integrated into the HPC environment, I think makes it a lot easier to attract people to the centralized research and provide a better user experience.
And we see that a lot with MATLAB as well, that they can run MATLAB in a really high performance way without writing any submission scripts. They can just start a MATLAB session with a powerful node with GPU, without GPU, and they don't even need to know that it's running on a back-end queuing system, for example. It's seamless.
Okay, and what are some common tools or software applications that are particularly beneficial for researchers in these non-traditional fields? I mean, we're talking about kind of new and emerging users, people who potentially have not been able to access HPC in the past.
I think MATLAB is one of our big tools. Jupyter Notebooks is also really something that is growing exponentially. But there are also a lot of visualization tools like ParaView, for example, that they can run large-scale visualization that they come with the data in place. You don't have to move the data. You can open it and get access to a powerful workstation to look at the data. There's some of the tools. RStudio is also something that is coming in, Visual Studio Code.
Yeah, we see a lot of usage of statistical and mathematical applications, MATLAB, Mathematica, SPSS, SAS. Things that you would traditionally run on a high-powered workstation, and giving people the ability to run that centralized for larger data sets, right? I think is something that will benefit a lot from this.
Okay, so how does centralizing compute resources benefit the researchers?
I think from a monetary point of view, not having to purchase high-powered workstations with the latest GPUs, specifically given the GPU cost lately, is something that will benefit researchers financially. And as long as you can make that centralized environment convenient to use, right? People normally like working on their workstations because they can touch it, they feel they have control over it. So if you want to realize the financial savings there, you have to provide an environment that's easy to use.
Then there can also be benefit for example, we have a large group of medical users that work on sensitive data. And there it could be beneficial to centralize that and keep the data in a single place and still offer them a nice environment where they can work with the sensitive data.
Oh, it's interesting. So it's not necessarily just simulation capabilities and kind of cost, but also kind of data security in some ways.
Yeah.
Okay, so
an interesting thing as well, just a side note here, that we have a lot of our old-time users are starting to use this as an environment to kind of keep their data, the state of their work. So they use terminals, but they use a desktop to consolidate the terminals.
Okay. What are the most critical steps for smaller research teams that are transitioning to HPC?
I mean, I really, as much as performance is important, I really think getting users on board with the environment is a key point, right? I think you see in HPC installation the success of Open on Demand as one of the ways to provide graphical access. And I think Xavier should talk a little bit about Cycle Cloud there in Azure as well, because I think it's a very, very similar tool. So the first step really is ideally meeting people where they are, right? Allowing them to to make minimal changes to their workflows and just provide them more performance. Now, this is not always the right thing to do, right? Sometimes you just have to change the workflow to get the most performance. But in order to show early benefits in HPC usage, getting them an environment that they can easily migrate into with things like Open on Demand or ThinLink with desktops, I think makes a lot of sense.
But I also think that we need to have, in our case, training is also essential to kind of give workshop on introducing the tools, because sometimes there is a preconception of HPC. We hear it a lot that, HPC center is so complicated. And you need to get information about that is not the case. It's actually much, much easier than you think. And we also have enabled, you can access the desktop environment through the web. And so there is basically no hurdles to the machine. But they still need to know that this is the fact, that it's easy to use.
Xavier, did you have any thoughts on this?
Yes. I think in addition, when you start a project, if you start from scratch, you need to think about your HPC infrastructure. And this is where the cloud can be an actor to ease up or make easier or seamless deployment of your HPC infrastructure. Open on Demand is also key for common access to your HPC resources, and it plays a big role in integrating applications and having a seamless experience for every users. Because the web interface will allow people to work from anywhere.
So I guess there are kind of two parts of HPC which are quite distinct there. One is kind of getting people access to the resources in the initial, in the initial instance, and kind of making that as seamless as possible. And then there's the kind of more fine tuning and kind of getting the largest efficiency out of your code that you can, which is something that's more for the more advanced users. But I think maybe in the past we just kind of looked at it as a very difficult thing, as Jonas was saying. Whereas there are ways to democratize access and make this easier for people to use in the first instance.
Yeah, I think in the past there was. Go ahead.
Yes, sorry. I mean, if we look at our users here, the users that actually are developing and fine-tuning code are decreasing. We provide a lot of prepackaged high-performance packages that most users use. So that those researchers that actually develop their own code is fewer and fewer.
Yeah, I see that from my perspective as well, and then being able to, what did I want to say? I'm good.
Is that something that is a positive? Do you need people in HPC developing your code? Obviously, to a certain extent, you do. But in a university sector, is that is the fact that less people are kind of fine-tuning their code? Is that just a consequence of the codes being more well optimized in the first instance, or is that something that's a challenge further down the road where we potentially have less people with a particular set of skills?
I mean, it is a challenge because there are things that needs to be developed, and there is also a trend that people are moving away from the traditional classical computational languages like C++, Fortran, going to Python, and we still need to have competence in the tuning parts, and also helping out perhaps if there is a new code coming out that does something a different way, we need to have these skill sets to be able to take them further as well. And that is harder to find, that skill set.
I think specifically recruiting new users into HPC is harder, right? Because I think, as you said, everybody has the preconceived notion that HPC is super hard to do, and you have to be an expert on day one. And I think if we don't do a better job in recruiting computational scientists to really develop code, I think this is going to be I think is already a major problem, but it's going to become an even bigger problem in the future. So the more we can help people into those environments and then show them that it is worthwhile to develop your own code. I think it's great that more people make use of HPC today than 15 or 20 years ago. We just need to now also transition them along and get them more skills.
Yeah.
Is that a challenge that needs to be is then faced by kind of academia? Is academia the place to solve that challenge and to get people those skills? Is it something that they need when they go out into industry or out into the workforce, or is this something that needs to be kind of addressed in multiple areas?
I think it has to be solved in multiple areas, and not only by academia, but also we have a role to play to kind of educate HPC users and also developers of software packages in the scientific field. But I think also the industry needs to be aware that they need that skills in the future.
Yeah.
Okay, on to the. Oh, carry on.
Sorry, I think this is also a challenge between, especially with the AI research, in between the high level of tooling you are proposing to the researchers and the deep level of tuning. So I mean, and this should be covered by tooling. That these tooling should be easy to use and embedded in the languages. And I think this is what some of the hardware vendors are trying to fill, but also the open source community to make this even easier to use.
Yeah, running TensorFlow out of a Jupyter notebook is easy. Running TensorFlow well out of a Jupyter notebook is hard.
Yeah.
And this is where
I completely
container can
agree.
help also. Yeah, and this is where container can help also to make your installation and deployment easier if your container are not too large.
Okay, so what happens if the container is too large? What kind of challenges can that throw up?
That will be the download data of your containers from remote registry to the local machine. Keeping the cache locally in the machines will be also a challenge if you have too many containers, too many large containers. So it becomes a management headache then.
Okay.
But I agree. It's nice to see container adoption among the end users, and it's nice to see that it's much easier now to use containers in an HPC environment, and have more users use them.
Yeah. But then there is also a question of training again. I think training the user and how to use containers. So we have had some courses on a national level here to further that knowledge, because it's a hurdle to start developing containers.
And then you have the container integration with job schedulers and your HPC infrastructure. And this is where Slurm has a good story with container integration, which make and with en route, for example, you can download containers, or Slurm can download containers automatically to the local machines and start your job in the container. So mostly for the end user, there's no disruption between what they are running locally and what they can run on a cluster, for example.
Is that a feature, or is that something that the community's been asking for then? Is Slurm the first one that's taken the step to kind of integrate, containers and make them more accessible, more easy to use?
I think it's a good step that they're taking to make it automatic, because you can integrate that so it becomes transparent for the user as well. But
I think it's also driven by the AI needs, because there are a lot of containers pre-ready to run training workloads, and so it's an easy way to start your simulation jobs. So the market was moving towards containerization of applications, and I think we will see more and more of these in the future. So you talk about MATLAB, for example. So I met MathWorks at Supercomputing, and they can run MATLAB in a container, and this can be integrated with OpenOnDemand. So you can have a web interface to start your MATLAB environment on a remote desktop, and then use this seamlessly.
Yeah, given the complexity of a well-performing AI software stack, containers may be the only solution there. Teaching end users how to make sure they combine the correct drivers with the correct libraries and the correct frameworks is no easy task. So
sometimes we have used containers too. Sorry.
No, but this is where you can provide a base container that match your infrastructure. So you know that you have the right GPU drivers, the right MPI libraries in it, and then the end users will build on top of it.
Okay, so
we use a lot of containers.
Carry on.
We use a lot of containers for building software that is really insanely complicated to build, and then we provide them to the users without them knowing that it is a container. So it's a way of providing more software as well as a HPC center.
Okay, so it's really allowing you to kind of tailor your infrastructure to these specific user needs, and maybe obfuscate some of that complexity that if they had to do it themselves.
Yeah.
Okay, so on to the next topic. How can researchers, efficiently manage and share large data sets in a HPC environment?
So I think in the traditional way is shared project spaces, right? I think as Jonas alluded to earlier, and I mean that's something that has worked well in traditional HPC environments. Some now we will now allow users to also mount those project spaces on their workstations for easier for data sharing and specifically ingesting data from endpoint devices. I'd be interested, Xavier, what's the cloud story there?
The cloud story is I would say the same than on-premises, with the difference that once in the cloud you can build sharing environment around. So that, for example, you can use system like Globus for having a shared namespace. The fact also that when you are in the cloud, or for us, Microsoft in Azure, you can easily move data from one region to another region, or so that you can provide a lower latency access for people on a remote location, for example. This could be important for distributed teams. And then once you're done, you can move back your data on premises if you want, or leave it in the cloud in a cold archive, so that you save no cost.
We are looking at we have a accelerator here close by called Max4, and they generate super amount of data that needs to be transferred, and we are still looking at good ways of transferring data between our centers. And we haven't found really good tools, so it's still a lot of manual transfer. But then when they are in our center, then it's easier again. But having a easy-to-use web-based interface for moving data, that is something we're looking into now.
Is data, is that something that researchers should evaluate? When they're looking at platforms that suit their needs, whether it be kind of on-premise or looking to the cloud to achieve that.
Yeah, I think everybody has heard the story of research teams putting in a next generation sequencer, and then all they have is 100 megabit Ethernet into that building. So I think I think evaluating the data need should be one of the first things you do with new instrument, as Jonas said about particle accelerators, or I mean even just high throughput microscopes, right? Or next gen sequencers produce so much data now, and vendors do a good job of shipping local caches, and so you can do a little bit of local processing, but at some point you have to move it off. And then the earlier I think you talk to the infrastructure people, the better.
Yeah, we have several examples where we basically have gone into argument with research groups that have gotten a new instrument where they didn't take into account the data transfer and the local storage that they needed, and then they went to us. So we have data we want to transfer to you now, and there is no infrastructure, and they need to plan that from when they apply for the instruments, infrastructure for connecting the data and making it available.
Okay, so I guess, as you mentioned in the beginning, it's becoming easier for scientists and researchers to create data. So I guess there's lots of people who potentially, even just a few years ago, they maybe didn't have these type of data challenges in terms of data movement and processing analysis as well. So I guess what you're saying for them is that they need to kind of speak to their infrastructure teams and kind of identify these problems as soon as possible in order to be able to support that change.
Yes, that's really important.
And I mean, I don't want to minimize the growth in computational demand, but I almost think the growth in data is a much harder problem to solve for end users. Computation is something that, or computational needs, I think, are well understood over the last 20, 30 years. But now the availability of data and then data movement, data provenance is a much, much harder problem to solve outside of leading edge science. Right? If you are CERN and you have a couple of years of planning for data delivery and things, you've got that solved. But if you are a small research team that just acquired a sequencing machine or a high-throughput microscope, then that's a much harder problem to solve.
Yeah.
How can modern cloud or modern HPC platforms, whether that be cloud or kind of centralized remote access platforms, ensure ease of use for researchers who do not have a background in IT or system administration?
Oh, you have to work hard. You have to make sure. But it is, you have to have usability in mind all the time. And when I started in HPC, everything was about the terminal. You log into the terminal, you did everything with terminal, you transfer file with a terminal. And then you also see a lot of other users that have never seen that. And I think you need to work on all the steps, how you get access, how you log in. And then when you're on the desktop, you need to make sure that you have easy to use tools to be able to submit jobs, have good documentation, and work with it all the time and improve it. Look at the support tickets. What are the kind of burning needs that the user have? And then look at, can we develop something that is easy to make that process easier? So that's my feeling. Yeah.
As we cater to new users or younger users in particular that have not grown up on operating systems where you had to use a terminal to do things, right? Who have grown up on iPads or now the modern macOS and Windows desktops, giving them a graphical environment, for example, web-based like Open On Demand offers, is key for picking them, for helping them move from the environment that they know into the central one. And I will get on my soapbox for a minute here. Jonas has a similar system at his university. There is a number of universities that have really started using desktops as a way to provide a gateway to an HPC system. Of course, built on a number of different products, ThinLink being one of them. But the concept of having a desktop and then seeing the HPC system as an extension to that is something I think that's worthwhile exploring, specifically for new users that are coming from desktops. Because then, not just as Jonas said, it's even something for older users where you can have a number of graphical terminals open without having to deal with things like screen or no hub to keep it running for a long period of time. But you're getting all the benefits, and you're giving users something that they expect, right? The ability to basically walk away from your desktop and come back a day later and have everything still there like you have on your laptop is something that people just expect. And if an HPC system doesn't deliver this because of efficiency, right, it makes sense. But it's just harder for users to get used to this. And the more, I think, exploring some new usage concepts like web-based access, like graphical-based access with desktops, is something that earlier there used to be a lot of R&D in that area. I don't think we're doing enough research and development and new user interfaces currently to really lower the barrier of entry.
And also this is where you want to match interactive work with batch work. So how to seamlessly integrate those. And I think this is also why we have the collaboration with Sendio, so that with ThinLink running on Azure, you can connect to a Slurm cluster that can be easily created. That's what I'm calling fungible computing, where you can create fungible Slurm clusters easily connected to ThinLink, run your jobs, or after copying your data. And then once you're done, you can tear down everything. It's also another way of working without disrupting the end users' day-to-day work. And I think this is most important, because if you move to a system which is, for example, more software as a service oriented, the end users may have to change these habits, and the learning curve can take some time. While when you are using the same day-to-day tooling, then the learning curve is immediate and the usage, and then your benefits will be immediate as well.
And I think sometimes it's unavoidable to change your habits to take full advantage of an HPC system, right? I'm not saying we shouldn't evolve, but I think it's much easier to convince users to change their habit once you have them in an environment where they see the benefit, right? If they can get quickly to running their first interactive job on a system and then they see the power of it, it's much easier to talk to them about education and changing their workflows.
Yeah.
So we're kind of looking at overcoming that initial learning curve then, and having tools which are really easy to use and kind of familiar to people who potentially haven't used a terminal in the past, that can then use those tools to access HPC resources for the first time.
Yeah, and I think it pains me to say, but I think the majority of users on HPC systems will have never seen a terminal before, right? Yeah. And that, I think we need to face that reality a little bit, and really helping them, which again, right, I think we need to educate people into that terminal, but it's just hard if that is your very first step that you need to take. Then you're just perpetuating the myth that HPC is hard to use.
We can provide a terminal in a web browser.
Yeah, exactly. Yes.
But I think you shouldn't see the terminal as a solitary tool, but a combination. The desktop, the terminal is a work environment, and to help the user to kind of script their workflows and see the terminal as a tool. But there's still the access is the desktop. It's a way into that.
What resources or training are available to help researchers, or engineers, kind of get up to speed with HPC and kind of get that so they can start to use these tools? Particularly, I guess, in academia, are there any tools that you guys use with students or in academia, or alternatively on the cloud side of things?
So in academia, we give a lot of training as part of our collaboration on a national level, and we provide introduction to the shell, the terminals, and how to use Linux. We give introductions to how to manage storage and work with that. And also we provide a lot of documentation in addition to that. We would like to do more on video, but we haven't kind of come really full circle on that, but we are working on that as well.
I think I want to call out maybe the software carpentry and the data carpentry initiatives, which make those teaching materials free to use for everyone. It's nicely structured. We're leveraging some of that material here, and that works equally well in industry.
Yeah.
And I'm sure Azure offers plenty of training on the cloud, right?
Yeah, there are many courses, but we need to do a better job for HPC in the cloud as well, training, because an HPC system in Azure will be an end-to-end system. So you need to build a full infrastructure first before running your first job, and this is where why we are building this offering. Cloud workspace for Slurm, for example, which can create these fungible Slurm clusters in minutes, while before people had spent days because they need to learn the platform, understood which blocks to use, what will be the impact. We have prepackaged all of this, so it's immediately available. But training is still needed for sure.
I have a question kind of more specific, I guess, to Cloud HPC. But how does Cloud HPC ensure reliability, especially for kind of long-running simulations or critical research tasks? Are there any challenges there?
Sure, I can answer that. So in Azure, we have real HPC hardware. So we design hardware for the cloud, which means that we have InfiniBand capabilities. And in addition to this, we have added a lot of health checks testing, both on the host level, but also when the node is being started by Slurm or with Cloud. So that, for example, if there's a bad InfiniBand cable, we can detect that when the machine is starting, and the machine won't be added to your job. And so that will ensure a minimum at the beginning that you are in a healthy state. And during the jobs, those nodal checks can be run as well regularly or in between jobs to make sure that, and this is especially happening with the large GPU machines, that you have no ECC errors or the GPU are healthy as well. So we have customers running very long running jobs. But I would say the same will apply for on-premises, where if you run very long running jobs, you may want to checkpoint regularly because anything can happen at any time. So you want to be able to restart from a checkpoint state in order to avoid losing or wasting the previous time.
Okay.
In our environment, we have a maximum limit of 7 days for long running jobs. And that is just because we need to be able to make emergency updates and stuff on the machines. So that's why we have this limit. But so we also encourage users to do checkpointing and write down data at regular times.
Yeah, I guess good practice is always going to be part of that process to ensure kind of reliability of your own jobs.
Yeah.
And checkpointing can be challenging sometimes, because if you checkpoint too often, you will generate two more data, and then the bandwidth the bandwidth generated can be very high, or the throughput needed can be very high. So you need to balance between checkpointing, and while you checkpoint, you are not doing computation. So then you are paying for computation resources while you are doing data movement. So you need to find the right balance to know exactly when you can checkpoint and how often you check.
Yeah.
And kind of looking ahead, what emerging HPC technologies or trends should researchers watch for in the next few years?
Good question.
It's got the crystal ball. There's always one of these.
Yeah.
Carry on.
One thing I think that is a bit of a you see a trend now is the switch to ARM, and that is something we have to consider in regards to software as well, because we have a lot of software that's built and tested for x86, and I think we will see more ARM system coming in, and that we need to think about that. Then quantum, I really still have to learn more about quantum computing, but I think that is also some interesting things coming.
I think the need for GPUs won't go away anytime soon, right? Given how much investment has been put into the GPU ecosystem, and also given how AI is now really used in a lot of fields of science, maybe not as the main driver, but as part of a workflow. So I think seeing GPUs, maybe seeing AI specific accelerators roll out to a larger audience is something to look out for.
Yeah, and especially the AMD GPUs, which are going to compete with NVIDIA GPUs. So those will be need to balance the competition between both. I agree with ARM also would be also an important asset to look at. And anything around optimizing data movement or data storage or data transfer will be, because data will keep growing, and data volume is growing faster than the computation we can provide. So this is still building a global namespace, how you can share data across multiple regions, that will be key, because we are more and more working in distributed areas, and also because even for HPC centers, you are constrained by power capping. So you need to distribute your systems across several locations.
Yeah.
And I think coming back to maybe AI specific accelerators, their cloud has a role to play, right? If you can gain access to one of those accelerators in the cloud environment, for testing purposes and being able to test multiple implementations, that would be nice.
Yeah, especially that the collaboration we have with NVIDIA AMD, we can provide new hardware in advance of the market compared. So that can be a game changer.
Yeah, sometimes you build hardware that won't be available to the broad market at all.
Maybe.
Yeah, for sure. I think I've had this kind of use with a kind of discussion around quantum as well, that kind of being able to access kind of exotic technologies through the cloud is something that allows you to kind of test out these things without making a large investment up front. So that's certainly a good way to kind of test a technology without get your feet wet without kind of making that huge investment.
Yeah.
But I think for quantum, it's not only about the hardware for the quantum. It's also about algorithm. So you can today you can build a quantum software without a quantum computer, and in some areas this have been improvement in the process as well. So it's another way of thinking about the algorithm.
Yes, exactly, like quantum simulators. Yes, I think, yeah, for sure. There's a lot of work to be done kind of algorithmically, right? So giving people access to these tools and allowing them to build their algorithms now and get started with it is going to pay dividends when quantum computing becomes more ubiquitous.
Correct. Yes.
Great, thank you very much for this informative discussion. We're now going to move over to our short question and answer session. So a question from me first. Can you share a success story where centralized resources or cloud computing kind of accelerated a research project or kind of led to new discoveries?
I have one that I can start with, which we have a lot of fun with. So a couple of years ago, we were approached by our archaeologists, and they had been buying bigger and bigger workstations for their 3D reconstruction work because they're flying drones. And they have been flying over Pompeii, they're flying over Sweden, and the cameras are getting bigger, they have bigger sensors, and they generate tons of data. And we help them to get their software on our systems to be able to actually perform their work. And they have also used our systems in the field by having this central location they can connect to and do the calculations when they were in the field and have access to these powerful resources. And that has been really a success story. And the images and the visualizations are really cool to look at as well. And you walk around in Pompeii with a millimeter resolution. That is kind of cool. And they have run it, most of the reconstructions on our clusters, using both GPUs and CPUs.
Yeah, I'll pick an example that's not quite on the high end and doesn't need as much resources as what Jonas was talking about. But we had students from our business school who were working with nonprofits in Africa to help them service some of the wells and repair infrastructure. And for them, they basically had to figure out a schedule of the teams and which of those villages to visit, which is basically solving traveling salesmen, right? Not the easiest thing to do. And they were able to really take advantage of our infrastructure, specifically our research desktop, where they could install the software themselves graphically on those machines, run the solvers, which was a moderately parallel problem. But it ran for a good week and a half. So for them to just be able to use their laptops for something else while also running a week and a half long computational experiment. And in that case, they didn't even have to talk to the IT people at all. They could get that all accomplished themselves. And that's certainly something that without a centralized environment would have been hard to accomplish.
I will have one example is OpenAI, ChatGPT. It's not a secret that Azure was their main data centers. So yeah, this is really a groundbreaking discovery.
Yes, it's kind of hard to beat that example.
Yeah, he's just trumped everyone. How does Cloud HPC enable interdisciplinary research? You know, for example, kind of combining insights from computational biology and machine learning. I guess we should also, you know, we can also talk about kind of remote access to centralized resources as well, you know, as opposed to cloud.
Yeah, I can start with the cloud. So I think that the thing is to build a shared infrastructure of services and software that can be used for your interdisciplinary research. And so you can in Azure HPC, we have HPC machines to run your biology, computational biology jobs, for example. Then these results can be used by Azure Machine Learning, a software as a service solution, or a PaaS solution. So you can build this through mega building blocks, so that every people can collaborate easily with the best tool for the work they have to do.
I agree. When just having a mix of resources together in the same central location, that will enable people to use the different things together. I mean, we provide a lot of scientific software packages as well in our installation, and those are available for everybody, so you can use them interchangeable, and that enables you also to do combine research.
Yeah, I second that from Jonas, the ability to switch between CFD tools and structural mechanics tools and bioinformatics tools in the same environment with the same user interface is something that is easier done in a centralized environment than decentralized.
Yeah.
Yeah, and I guess, you know, any of these kind of, you know, secondary use cases for data, you know, whether they be whether they be research-based or not, you know, you need that infrastructure to be in place in advance in order to, before you make that decision that you want to use these things, right? So it comes back to, you know, understanding the needs of your potential, your computational needs, and then feeding that into the infrastructure decision-making process. So how can carry on?
This is also where Azure can be helpful, because in that case you can extend your current infrastructure with new hardware, new software, new capabilities, without breaking what have been done. Also, this centralized will be able to share the data between end users. So you have a central data gravity of your or data storage for all your data.
Absolutely, yeah. How can remote access to HPC, you know, efficiently handle kind of resource-intensive workflows, such as large-scale simulations or kind of AI model training?
I think we talked about the complexity of the AI software stack already.
Yeah.
I think if you can provide a well-working AI software stack in a centralized environment with all the training data you need, I think you make it a lot easier for people to experiment with training models, whether it's fine-tuning or actual training. If you can give them an environment where at least they can build on a well-working software stack.
Yeah. Does anybody else have any thoughts on that one, or shall I move on?
No, I think we covered some of those topics before. So.
Yeah. Okay. Finally, can tools, you know, such as cloud computing or kind of remote access to centralized resources, facilitate collaboration, you know, across institutions or even kind of globally distributed teams?
Yeah, I would say yes, because you can. We already do that. A lot of our projects, they have collaborate with researchers in the world, in the projects, and they can request accounts and access the projects and work together in teams. Because it's all available everywhere all the time, so that's easy to do.
Yeah, I mean, we have a number of research groups that will invite researchers from other countries and other continents to spend a couple of weeks at our institution, and then for them to be able to go home and still access the same systems without having to make copies of the data, right? We had a research team in neuroscience that was looking at functional MRI data, both with computational tools and then also visualizing it on our research desktop. And for them, the ability to do that in a performant way, both locally when at the institution and when at a conference or when going back to their home institutions, is something that works really well without having to copy the data. I guess we don't have the regional zones that Azure has, so you win in that one.
But even so, I see two challenges here. The first is the identity and authentication authorization. When you have multiple distributed systems, each one may use a different way of authenticate users. So you have to think about how can you integrate these authentication or user identities so that you stay secure and it's not a pain for the end users. And the other thing is the data movement as well, because if you have a new data set you want to study, you need to upload your data set. So in addition, you need to provide the tooling for you doing your data movement as well. But even so, the centralization is as Jonas and Robert explained, it's a big facilitator for people in distributing teams for sure.
Great, thank you. And this brings us to the end of today's webcast. This content will remain live on Scientific Computing World website at www.scientific-computing.com for the next 12 months. So please spread the word if you've enjoyed this discussion. Of course, please note that the live question and answer session will not function if you are listening on demand. Once again, thanks very much to our speakers, Robert Henschel, Xavier Pillens, and Jonas Lindemann, and of course to our sponsor, Sendio. Thank you all and goodbye.
Thank you.
Thank you. Thank you very much.